Picture standing at the edge of the ocean at night, staring into the endless dark. What you see is just the surface. Beneath those waves, hidden currents pull and twist in ways you'd never guess from shore. The universe works the same way. What we see, stars, galaxies, the glow of cosmic light, is only a fraction of what's really out there. The rest, an invisible tapestry of particles so strange, so elusive, they defy everything we think we know about physics. These aren't just minor details, they're the hidden architects of reality itself, shaping the cosmos in ways we're only beginning to unravel. Take dark matter, for example. It's everywhere, filling the spaces between galaxies, weaving through your body right now. And yet we can't see it, touch it, or even detect it directly. It's like trying to catch smoke with your bare hands. Then there are neutrinos, ghostly particles that pass through entire planets like they're not even there. Billions stream through you every second, leaving no trace. These aren't just curiosities, they're clues to a universe far stranger than we ever imagined. And the wildest part, these particles might hold the keys to secrets we haven't even dreamed of yet: parallel dimensions, hidden forces, even the fate of the cosmos itself. That's what we're diving into today. 30 theories about these hidden particles that will bend your understanding of reality. Some sound like science fiction particles that remember their past, shadows of alternate universes bleeding into ours, dark matter that could be an entire unseen civilization. Others challenge the very laws of physics, suggesting that what we call empty space is anything but. This isn't just about filling gaps in our knowledge, it's about stepping into a world where the rules are still being written. So if you're ready to explore the universe's deepest mysteries, the ones that lurk just beyond the edge of what we can see, let's begin. Actions might sound like something from a fantasy novel, but these elusive particles could be the answer to one of the universe's biggest mysteries: dark matter. Unlike the matter we're familiar with, actions are theorized to be unimaginably lightweight, almost ghostly in their interactions. They don't collide with atoms or emit light, which is why they've escaped detection for decades. But if they exist, they could be everywhere, flowing through the cosmos like an invisible river, subtly shaping galaxies with their gravitational pull. The idea of actions didn't just come out of thin air. They emerged from a deep puzzle in quantum chromodynamics, the theory describing how quarks and gluons bind together. Scientists call it the strong CP problem, a baffling observation that certain particle interactions don't behave the way we'd expect. Actions were proposed as a natural solution, a kind of cosmic fix that would restore balance to the equations. And if they're real, they wouldn't just solve that problem, they'd also fill the missing mass of dark matter. So how do you hunt for something that barely interacts with normal matter? Experiments like ADMX, the Action Dark Matter Experiment, are designed to catch these phantoms by converting them into detectable microwave photons using powerful magnetic fields. It's like setting up an ultra-sensitive cosmic net, waiting for the faintest ripple. Other projects like CAP in South Korea and Haystack in the US are joining the search, each refining the hunt with ever more precise technology. What makes actions so compelling isn't just their potential to explain dark matter, it's their elegance. Unlike other dark matter candidates, they tie together two seemingly unrelated puzzles in physics, offering a glimpse at how the universe might harmonize its deepest secrets. If discovered, they could rewrite our understanding of particle physics, revealing a hidden layer of reality woven into the fabric of space itself. While actions represent one elegant solution to the dark matter puzzle, there's another heavyweight contender in the race: WIMP, or weakly interacting massive particles. These hypothetical particles are the strong, silent types of the cosmos, carrying significant mass but almost never making their presence known. Unlike actions, which are feather-light, WIMP would be far more substantial, possibly dozens or even hundreds of times heavier than a proton. But here's the catch: despite their heft, they'd only interact with ordinary matter through gravity and the weak nuclear force, the same force behind radioactive decay. That means they'd pass through you, your house, and even the Earth itself as if none of it existed. For decades, WIMP were the darlings of dark matter research because they fit so neatly into existing physics. Theories like supersymmetry, which proposes every known particle has a heavier, invisible twin naturally predicted WIMP, would exist. It was almost too perfect. These particles could account for dark matter's gravitational effects while staying just out of sight. But finding them, that's where things get tricky. Scientists have turned entire mountains into detectors, like the LUX Zeppelin experiment buried nearly a mile underground in South Dakota. Shielded from cosmic rays by layers of rock and ultra-pure liquid xenon, these labs wait for the unimaginably rare moment a WIMP might bump into an atom. Think of it like trying to hear a single snowflake land in a thunderstorm. The sensitivity is staggering. LUX Zeppelin can detect interactions releasing energy equivalent to a mosquito's wingbeat. Yet, after years of searching, the results have been quiet. This silence has sparked fierce debate. Some researchers argue we might be looking in the wrong mass range, or that WIMP interact even more weakly than predicted. Others suggest dark matter could be a mix of particles, with WIMP playing just one part. Then there's the radical possibility: what if WIMP don't exist at all? The lack of detections has pushed physicists to re-examine long-held assumptions, opening the door to wilder ideas like dark matter being primordial black holes or even evidence of extra dimensions. But don't count WIMP out yet. Upgraded detectors and new technologies keep pushing the limits of what we can observe. Every null result narrows the possibilities, inching us closer to an answer. Whether WIMP are the ultimate solution or a stepping stone to something stranger, their story reveals how science grapples with the unknown, testing, doubting, and reinventing itself in the face of the cosmos's stubborn secrets. Neutrinos are already some of the most mysterious particles in existence, but what if there's another kind, one even more elusive? Enter sterile neutrinos, a hypothetical fourth flavor that could rewrite what we know about these cosmic phantoms. Unlike the three known neutrinos, electron, muon, and tau, sterile neutrinos wouldn't interact through any of the fundamental forces except gravity. They'd be the ultimate shadows, slipping through the universe unnoticed. Yet their presence might explain some of the most puzzling gaps in physics, from strange neutrino behavior to anomalies in deep space signals. The idea first gained traction when experiments detected unexpected patterns in neutrino oscillations, the process where neutrinos switch between their known types as they travel. The math suggested something was missing, a hidden player influencing the mix. Sterile neutrinos fit perfectly, acting as a kind of invisible conductor orchestrating the oscillations from behind the curtain. But the implications go far beyond particle physics. Astronomers have spotted a faint, unexplained X-ray signal at 3.5 kilo-electron volts emanating from galaxy clusters and other massive structures. One compelling explanation: sterile neutrinos decaying in space, releasing this energy like a whisper across the cosmos. Even more intriguing is their potential role in shaping the universe itself. If sterile neutrinos exist, their sheer mass, likely far greater than ordinary neutrinos, could have acted as an invisible scaffold in the early universe, guiding how galaxies formed. Picture a cosmic blueprint, invisible yet indispensable, directing where matter clumped together to birth the vast structures we see today. Some theories even suggest sterile neutrinos could be a fraction of dark matter's missing mass, bridging the gap between two of physics' greatest mysteries. The hunt for these ghostly particles is anything but easy. Experiments like Fermilab's Short Baseline Neutrino Program and Russia's Baksan Neutrino Observatory are pushing detector sensitivities to unprecedented levels, searching for the slightest anomaly that might betray a sterile neutrino's presence. Meanwhile, space telescopes like Chandra scrutinize that mysterious 3.5 kilo electron-volt line, looking for patterns that could confirm their decay. What makes sterile neutrinos so captivating isn't just their potential to solve multiple puzzles, it's the way they blur the line between the known and the unknown. They remind us that even the most well-studied particles might have secrets, and that the universe's greatest revelations often come from chasing the faintest signals in the dark. Magnetic monopoles sound like something straight out of a sci-fi novel: single, isolated magnetic charges, the north without a south, or vice versa. But these elusive particles weren't dreamed up for fiction. They emerged from one of the sharpest minds in physics. Paul Dirac, the legendary theorist who reshaped quantum mechanics, first proposed their existence in the 1930s while wrestling with a deceptively simple question: why do electric charges exist as standalone entities while magnetic ones always come in pairs? His math revealed something startling. If even a single magnetic monopole existed somewhere in the universe, it would explain why electric charge is quantized, appearing only in neat multiples of the electron's charge. It was as if the universe had left a hidden signature in its equations, hinting at a deeper symmetry waiting to be uncovered. The implications ripple far beyond Dirac's era. Grand unified theories, ambitious frameworks aiming to merge the electromagnetic, weak, and strong nuclear forces, predict that monopoles should have been produced in staggering numbers during the universe's earliest, hottest moments. These wouldn't be the delicate, theoretical curiosities Dirac imagined, but monstrously heavy particles, perhaps a quadrillion times more massive than a proton. In those chaotic first instants after the Big Bang, space itself should have been thick with them. So where are they? That's where cosmic inflation comes in, a theory suggesting the infant universe underwent an exponential growth spurt, stretching space faster than light in a fraction of a second. Inflation would have diluted monopoles like a drop of ink in an ocean, scattering them so thinly that finding one today would be like searching for a single grain of sand in a desert. Some models suggest there might be just one monopole lurking in our entire observable universe, yet the hunt persists. Experiments like Mo et al. At CERN use ultra-sensitive detectors to catch monopoles' telltale trails, while others scour ancient minerals for traces of monopoles that might have gotten trapped like fossils in Earth's crust. Even cosmic rays are scrutinized for signs of these magnetic ghosts. The stakes couldn't be higher. Finding a monopole wouldn't just validate Dirac's intuition. It could expose cracks in our understanding of fundamental forces, offering clues about how the universe chose its laws in those first fiery moments. What makes monopoles so captivating is their duality. They're both relics of a time when the forces of nature were indistinguishable and potential keys to unlocking physics beyond our current theories. They remind us that the universe's deepest secrets might not lie in what we can see, but in the voids between, where the echoes of symmetry and chaos still linger. Gravity is the force we know best. It keeps our feet on the ground and planets in their orbits, but at the quantum level, it's the universe's greatest enigma. While the other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, all have particles mediating their interactions, gravity stubbornly resists this framework. Enter the graviton, a hypothetical particle that could finally bridge Einstein's theory of general relativity with the quantum world. Picture it as the universe's quietest messenger, carrying gravitational influence in discrete, invisible packets, just as photons transmit light. String theory offers one compelling vision of how gravitons might work. In this framework, gravitons emerge as tiny, vibrating loops of energy, strings so small they'd make an atom look like a galaxy. These vibrations would correspond to gravity's pull, seamlessly weaving it into the quantum tapestry. The elegance is undeniable. String theory doesn't just accommodate gravitons, it demands their existence. Yet there's a catch. To make the math work, string theory requires extra dimensions, up to 10 or 11 curled into shapes too tiny to detect. It's a beautiful idea, but one that's notoriously difficult to test. Loop quantum gravity takes a radically different approach. Instead of particles or strings, it reimagines space-time itself as a fabric woven from finite, interwoven loops. Here, gravitons aren't independent entities but emergent properties of this granular structure, like ripples on a pond's surface. The theory trades extra dimensions for a universe where space and time are pixelated, with gravity arising from the quantum entanglement of these microscopic loops. It's a bold rethinking of reality, one that sidesteps the infinities plaguing other quantum gravity models. The stakes couldn't be higher. Unifying gravity with quantum mechanics wouldn't just solve a theoretical puzzle. It could revolutionize our understanding of black holes, the Big Bang, and even the nature of time. Some models suggest gravitons might leak into extra dimensions, explaining why gravity is so weak compared to other forces. Others propose that detecting gravitons, though staggeringly difficult, could reveal signatures of cosmic strings or other primordial relics. Experiments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, have opened new windows by observing gravitational waves, but catching a graviton remains a distant dream. The particle would be so faint that a detector the size of Jupiter might only spot one per decade. Yet the search presses on because gravitons represent more than just a missing piece. They're a gateway to seeing the universe not as a stage where physics plays out, but as something far stranger, a dynamic quantum dance where space, time, and gravity are all partners in the mystery. What if every particle in the universe had a hidden twin, an identical yet invisible counterpart, moving through a parallel reality right alongside ours? That's the startling premise of mirror matter, a theory suggesting an entire shadow universe of particles exists, perfectly mirroring ours but interacting only through gravity. These aren't just doppelgangers, they'd obey their own set of mirrored physical laws, forming stars, planets, even life, all completely undetectable to us except by their faint gravitational tug. It sounds like science fiction, but this idea could solve one of physics' most stubborn mysteries: why neutrons seem to live longer when trapped in experiments than when floating freely in space. The discrepancy in neutron lifetimes has puzzled scientists for decades. In lab experiments, neutrons bottled up in magnetic fields take about 14 minutes and 40 seconds to decay. But when neutrons stream through space, observations suggest they vanish faster, lasting only around 14 minutes and 38 seconds. That tiny gap, just 2 seconds, might not seem like much, but in particle physics, it's a glaring inconsistency. Mirror matter offers an elegant solution. What if some neutrons aren't decaying at all but slipping into this hidden realm, transforming into mirror neutrons that vanish from our detection? It's as if they're stepping through a one-way door into a world we can't see. The implications go far beyond neutrons. If mirror matter exists, it could account for the universe's missing mass dark matter without requiring new exotic particles. Instead of WIMP or axions, dark matter might simply be ordinary matter's mirror twin, woven into the fabric of space but forever out of reach. Picture two galaxies overlapping, one made of atoms we know, the other of mirror atoms, each oblivious to the other except through gravity's subtle whisper. This wouldn't just explain dark matter's gravitational effects. It could reveal an entire universe operating in parallel with its own chemistry, physics, and perhaps even mirror life. Experiments are already hunting for hints of this shadow world. Neutron beam facilities like those at the Institut Laure Langevin in France are searching for anomalies in decay rates that might betray a neutron's jump into the mirror realm. Others are scrutinizing cosmic rays for particles that seem to vanish without a trace. Even more tantalizing are proposals to detect mirror photons, light from mirror stars that might subtly leak into our universe, creating faint glows in deep space where none should exist. What makes mirror matter so compelling isn't just its potential to solve multiple puzzles at once. It's the audacity of the idea itself. a hidden cosmos, identical yet separate, challenges our very notion of reality. It suggests that everything we perceive, every star, every atom, every breath might be just one half of a grander, doubled existence. And if true, it would mean the universe has been keeping its biggest secret not in distant galaxies or quantum voids, but right beside us all along, invisible in plain sight. Imagine a universe where particles don't just exist in the three dimensions we know, length, width, and height, but ripple through hidden, curled-up dimensions too small for us to perceive. This isn't just a wild thought experiment, it's the heart of Kaluza-Klein theory, an idea that's been shaping physics for over a century. Back in the 1920s, mathematician Theodore Kaluza and physicist Oskar Klein proposed that if our universe had an extra, compact dimension, it could unify Einstein's gravity with Maxwell's electromagnetism in a single, elegant framework. But the real surprise came when string theorists revived their work decades later, revealing something astonishing. These extra dimensions might not just be mathematical curiosities. They could spawn entire towers of particles, each one a heavier echo of the particles we know, vibrating at different frequencies through hidden space. Think of it like a guitar string. Pluck it once, and you hear a single note, the fundamental tone. But the string also vibrates at higher harmonics, producing overtones too faint to notice unless you're listening closely. In Kaluza-Klein theory, every particle, electrons, quarks, even photons, could have its own set of these harmonic counterparts, each with a mass proportional to how tightly it vibrates in the extra dimension. The tighter the dimension, the heavier the particles. Some might be just beyond our current energy limits, while others could be so massive they'd only appear in the earliest moments of the Big Bang. So how do we hunt for something like this? The Large Hadron Collider, or LHC, is on the front lines. Scientists there scour collision data for strange, fleeting signatures particles that seem to vanish into thin air. These disappearing tracks could be the smoking gun of a Kaluza-Klein particle decaying into something invisible, like a graviton escaping into higher dimensions. Other experiments look for anomalies in gravity at microscopic scales, where extra dimensions might subtly weaken or warp its pull. Picture gravity as a force that normally spreads out in three dimensions, but if some of it leaks into a hidden dimension, its strength could drop off faster than expected over tiny distances. The implications are staggering. If Kaluza-Klein particles exist, they wouldn't just confirm extra dimensions, they'd rewrite our understanding of mass itself. The Higgs boson gives particles their mass, but Kaluza-Klein partners could derive theirs purely from how they vibrate in unseen geometry. It's a reminder that the universe's building blocks might not be fundamental at all, but notes in a higher dimensional symphony we're only beginning to hear. What makes this theory so compelling is its audacity. It doesn't just add new particles to the menu. It suggests everything we've ever observed could be the lightest, simplest version of something far richer. And if we're lucky, the next collision at the LHC or some ingenious tabletop gravity experiment might finally reveal the first echo from those hidden dimensions, proof that we're not just living in a universe, but within its shadow, surrounded by layers of reality folded too small for eyes to see. At the very edge of what physics can describe lies a realm so small, it defies imagination, the Planck-scale. Picture a length 100 billion times tinier than a proton, where space itself stops being smooth and continuous, instead churning with a seething quantum foam. Here, particles might flicker in and out of existence so quickly they barely register as real. These aren't just hypothetical specks, they could be the fundamental building blocks of spacetime, stitching together the fabric of reality at the most basic level. This quantum foam isn't just a wild idea, it's a prediction of combining quantum mechanics with general relativity, two theories that famously refuse to play nice. At scales this small, spacetime would become a turbulent, ever-changing froth, with tiny wormholes and black holes popping into existence and vanishing in less than a Planck second. That's 10 to the minus 43 seconds, a time span so brief, even light couldn't cross a single atom in that duration. These fluctuations would be governed by Planck-scale particles, entities so ephemeral they'd make neutrinos seem as solid as bricks. The catch: we can't directly observe anything this small. The energy required to probe the Planck scale is a quadrillion times beyond what the Large Hadron Collider can muster. But nature might have left us clues in the most violent events in the cosmos: gamma-ray bursts. These titanic explosions, thought to arise from collapsing stars or colliding neutron stars, fling high-energy photons across the universe. As these photons travel billions of light-years, something peculiar happens. The highest energy ones arrive slightly later than their lower energy counterparts. One possible explanation: quantum foam. If spacetime is indeed grainy at the Planck scale, high-energy photons would stumble over these microscopic bumps, slowing down ever so slightly. It's like running through sand: the harder you push, the more resistance you feel. This delay, known as Lorentz invariance violation, could be our first indirect glimpse of Planck-scale physics. Experiments like the Fermi Gamma-Ray Space Telescope have spent years analyzing these bursts, hunting for deviations that might betray the foam's texture. But there's another twist. Some theories suggest Planck-scale particles could act as primordial seeds for spacetime itself, their interactions defining how the universe chooses its geometry in the first moments after the Big Bang. In this view, the smooth expanse of space we see today would be an emergent property, a kind of quantum averaging of countless microscopic fluctuations. It's as if the universe is a vast cosmic tapestry woven from threads so fine we'll never see them directly, only sense their collective pattern. What makes these ideas so thrilling isn't just their mind-bending scale, it's the audacity of the questions they raise. Are we living in a universe where space itself has atoms? Could gamma-ray bursts be our telescopes into a realm beyond measurement? The answers might lie in the next cosmic cataclysm, waiting for us to decode its whispered secrets. Among the most elegant solutions to the dark matter puzzle lies a particle born from symmetry itself, the neutrino. This hypothetical heavyweight emerges from supersymmetry, or SUSY, a theory so mathematically beautiful it's been called physics' castle in the clouds. SUSY proposes that every known particle, electrons, quarks, photons, has an undiscovered superpartner, a shadow twin with different spin properties. The lightest of these superpartners, often the neutrino, would be stable, electrically neutral, and nearly invisible, making it a perfect dark matter candidate. What sets neutralinos apart isn't just their stealth, it's how they could reveal themselves through annihilation. Picture two neutralinos colliding in the depths of space. Instead of bouncing off each other, they'd obliterate in a flash of gamma rays, a fireworks show of high-energy light. Telescopes like NASA's Fermi have scoured the sky for these telltale bursts, particularly near the Milky Way's center where dark matter is thought to concentrate. A faint, unexplained glow called the galactic center GVXS has fueled speculation for years. Some researchers argue it could be neutralino annihilation, though others point to mundane sources like ancient pulsars. The mystery deepens when we turn to the Large Hadron Collider. SUSY elegance hinges on solving the naturalness problem, the puzzling weakness of the Higgs boson's mass compared to the immense energies of quantum fluctuations. Superpartners should balance these scales, keeping the Higgs stable. Yet despite smashing protons at record energies, the LHC has found no trace of SUSY particles. Detectors like ATLAS and CMS have ruled out vast swaths of potential neutralino masses and interaction strengths, leaving theorists grappling with two possibilities. Either SUSY particles are far heavier than expected, or nature has chosen a different path entirely. This absence hasn't killed SUSY, it's forced a reinvention. Some models now propose stealth SUSY, where superpartners decay in ways that evade detectors. Others suggest neutrinos might cluster differently than standard dark matter, leaving subtler fingerprints in galaxy rotations. There's even wilder speculation. Perhaps neutrinos aren't the lightest sussy particles after all, but share the stage with other elusive actors like gravitinos. What keeps physicists returning to neutrinos isn't stubbornness, it's the theory's uncanny ability to tie together cosmic puzzles. From dark matter's grip on galaxies to the delicate tuning of the Higgs field, SUSY offers a framework where these disparate threads weave into a coherent whole. Whether neutrinos are waiting just beyond our current energy, reach, or belong to a grander, undiscovered symmetry, their story exemplifies science at its most ambitious, chasing shadows in the hope of illuminating everything. What if the universe has a speed limit and some particles simply ignore it? Tachyons are one of physics' most controversial ideas, hypothetical particles that don't just approach the speed of light but start their existence already moving faster. Unlike ordinary matter, which requires infinite energy to reach light speed, tachyons would need infinite energy to slow down to it. Their secret, imaginary mass, a concept so bizarre it seems ripped from a mathematician's fever dream. In Einstein's equations, mass is usually a positive, tangible value, but tachyons would flip this on its head. Their squared mass would be negative, making their mass itself an imaginary number, like the square root of -1. This isn't just a quirk of math. It's the key to their faster-than-light motion, allowing them to surf the fabric of space-time in ways that defy intuition. The implications ripple far beyond speed. If tachyons exist, they'd challenge causality itself, the bedrock principle that cause must always precede effect. Picture a tachyon message sent from Earth to a distant star. In some reference frames, observers might see the signal arrive before it was even sent, creating paradoxes where events unfold in reverse. It's the ultimate cosmic rewinding, where a bullet could leave the wound before the trigger is pulled. These paradoxes aren't just philosophical puzzles, they're why many physicists dismiss tachyons as mathematical ghosts rather than real entities. Yet the idea persists because it pushes us to ask, are the laws of causality as immutable as we think, or could the universe have loopholes we haven't discovered yet? Ironically, tachyons' most tantalizing application isn't in breaking physics but in bending it, specifically in warp drives. The Alcubierre drive, a speculative faster-than-light concept inspired by general relativity, relies on warping spacetime to create a bubble where a ship rides a wave of compressed space ahead and expanded space behind. But here's the catch: generating this bubble would require negative energy, something exotic matter like tachyons might provide. While no known physics allows stable negative energy, the possibility remains open in quantum field theory, where phenomena like the Casimir effect hint at fleeting negative energy densities. Tachyons, with their imaginary mass, could theoretically stabilize such a bubble, though the engineering hurdles are, to put it mildly, astronomical. The hunt for tachyons has been as elusive as the particles themselves. Early experiments in the 1970s searched for tachyon signatures in cosmic rays, while modern particle colliders have probed high-energy collisions for anomalies that might betray their presence. So far, no luck. But absence of evidence isn't evidence of absence, especially when dealing with something as slippery as a particle that, by definition, might be impossible to catch. Some theorists suggest tachyons could be hiding in plain sight, not as traditional particles but as disturbances in quantum fields, flickering in and out of existence too quickly to detect. What keeps tachyons alive in scientific discourse isn't just their shock value but their audacity. They force us to confront the edges of our understanding where mathematics and imagination collide. Whether they're ultimately proven real or relegated to the realm of thought experiments, tachyons remind us that the universe's rulebook might still have pages we haven't turned or even written yet. And in that uncertainty lies the thrill of discovery, the chance that somewhere beyond the limits of light, physics might have surprises waiting. Glueballs sound like something from a science fiction arsenal, but these theoretical cosmic objects could be among the heaviest and strangest forms of dark matter. Unlike the individual particles we've discussed so far, cue balls are macroscopic, meaning they could span sizes from a speck of dust to a small planet. Born from supersymmetry, they're not made of atoms or quarks, but of squarks, hypothetical superpartners of quarks, or other bosons, all bound together in a stable, bubble-like configuration. What keeps them from dissolving? A delicate balance between energy and charge. In the early universe, as temperatures cooled, regions of space might have become trapped in a false vacuum state, their quantum fields unable to transition to the lower energy state we experience today. These pockets could have crystallized into cue balls, cosmic relics so dense and stable they've lasted nearly 14 billion years. Their sheer mass makes them formidable dark matter candidates. A single cue ball could weigh as much as an asteroid, yet interact with ordinary matter only through gravity, or in some models via rare catastrophic collisions. Picture one drifting through Earth. If it's electrically neutral, it might pass through unnoticed, but if it carries even a tiny charge, the encounter could release enough energy to outshine the sun. That's why detectors like Super Kamiok and in Japan scan for sudden, unexplained flashes of radiation deep underground, hoping to catch the telltale burst of a cue ball's demise. But cue balls aren't just dark matter curiosities. They might hold the key to one of cosmology's biggest puzzles: why the universe has more matter than antimatter. During baryogenesis, the process that tipped the scales toward matter, cue balls could have acted as factories, their decay producing an excess of quarks over antiquarks. Some theories even suggest they seeded primordial black holes, collapsing under their own gravity to form the universe's earliest gravitational traps. It's a staggering thought. These exotic objects might not just lurk in the cosmos but have shaped its very structure. The hunt for cue balls straddles the line between particle physics and astronomy. Cosmic ray experiments search for their rare decays, while telescopes look for distant gamma-ray bursts that match their predicted signatures. Even gravitational wave detectors could play a role. A cue ball collision would ripple spacetime with a frequency unlike any known astrophysical event. What makes cue balls so captivating is their duality. They're both relics of a symmetry-laden early universe and potential architects of the one we inhabit. Their existence would prove that dark matter isn't just a sea of invisible particles, but could include monstrous, ancient structures, frozen echoes of a time when the laws of physics were still writing themselves. Dark photons lurk in the shadows of particle physics, not quite light, not quite dark matter, but something eerily in between. Imagine if the universe had a hidden communication channel, a secret line connecting the ordinary atoms around us to the invisible dark matter permeating space. That's the promise of dark photons, hypothetical particles that might serve as cosmic translators between these two realms. Unlike regular photons, which mediate electromagnetism, dark photons would carry a dark force, interacting feebly with normal matter while potentially shaping dark matter's behavior in ways we can't yet see. The theory emerged from a simple yet profound question: why does dark matter seem to clump and interact in ways gravity alone can't fully explain? Just as electromagnetism sculpts galaxies and stars through charged particles, a dark force mediated by dark photons could be organizing dark matter into intricate structures. These particles wouldn't just bridge the gap between visible and invisible worlds, they might also explain baffling anomalies, like the unexpected excess of high-energy positrons detected by experiments like MS-02 aboard the International Space Station. Could those positrons be the debris of dark photon decays flickering into existence before vanishing again? Hunting these phantoms requires ingenuity. Experiments like the Heavy Photon Search, or HPS, at Jefferson Lab fire intense electron beams into thin targets, hoping to catch a dark photon's fleeting signature. Unlike regular photons, which leave clear trails in detectors, dark photons would hide by decaying into pairs of electrons and positrons just millimeters from their creation point. It's like searching for footprints that vanish almost as soon as they're made. Other projects like NA64 at CERN and dark light in the US take different approaches, slamming particles into materials designed to absorb every scrap of energy. If energy goes missing without explanation, it could mean a dark photon spirited it away into the invisible sector. The stakes are dizzyingly high. If dark photons exist, they'd open a portal to dark matter's hidden interactions, revealing a universe far more interconnected than we imagined. They could even hint at why dark matter outnumbers normal matter 5 to 1, perhaps because dark forces sculpted it more efficiently in the early cosmos. But the puzzle has layers. Some models suggest dark photons might also solve the proton charge radius anomaly, where measurements of the proton size disagree depending on the method used. A dark photon subtly altering how electrons and protons interact could reconcile these discrepancies, tying together mysteries across vastly different scales. What makes dark photons so tantalizing isn't just their potential to solve multiple puzzles at once. It's the audacity of the idea that an entire sector of physics hums just beyond our perception, its influence woven into the fabric of reality. Every experiment that comes up empty narrows the possibilities, inching us closer to knowing whether this shadow force is out there, or if the universe's secrets run deeper still. Imagine a particle so shy it changes its very nature depending on who or what is watching. That's the essence of chameleon particles, hypothetical entities that alter their mass based on the density of their surroundings. In a crowded environment like Earth, these particles would be incredibly light, slipping through detectors unnoticed, but in the vast emptiness of space, they'd grow heavy, potentially exerting enough gravitational pull to explain dark energy's mysterious influence on cosmic expansion. It's as if the universe has been hiding one of its most fundamental players in plain sight, camouflaged by the very laws meant to reveal it. The theory stems from an ingenious solution to one of physics' greatest headaches. Why hasn't dark energy, the force accelerating the universe's expansion, shown up in lab experiments? If dark energy permeates all of space, its effect should be detectable everywhere. Yet here on Earth, it's nowhere to be found. Chameleon particles offer an elegant fix. As scalar fields, meaning they have magnitude but no direction, their mass isn't fixed but scales inversely with local matter density. Near Earth, surrounded by atoms and air molecules, the field's mass would balloon, making its effects vanishingly small. But in the near-perfect vacuum between galaxies, the field's mass could drop to near zero, allowing it to stretch spacetime like an invisible hand. This adaptability makes chameleon particles devilishly hard to track down. Traditional particle detectors, built to catch interactions in dense environments, are practically blind to them. That's where atom interferometry comes in, a cutting-edge technique that exploits quantum mechanics' wave-particle duality. By splitting clouds of ultra-cold atoms and measuring how their paths bend, scientists can hunt for faint forces that might betray a chameleon's presence. Experiments like AEON in the UK and MAGI's in the US are pushing this method to unprecedented precision, effectively turning individual atoms into exquisitely sensitive force detectors. But the implications go beyond dark energy. Some models suggest chameleon fields could mediate a fifth force, subtly altering gravity's behavior at microscopic scales. This would violate Einstein's equivalence principle, the idea that inertial and gravitational mass are identical, a cornerstone of general relativity. Tests using torsion balances, which measure twist caused by tiny forces, have placed stringent limits on such deviations. Yet the hunt continues, because if chameleons exist, they wouldn't just solve the dark energy puzzle, they'd rewrite our understanding of fundamental forces. What makes these particles so captivating isn't just their stealth, it's their audacious versatility. They could be the missing link between the quantum world and cosmology, between the infinitesimally small and the cosmically vast. And if detected, they'd prove that the universe's greatest secrets aren't just hidden in distant galaxies or powerful colliders, but woven into the fabric of our everyday reality, waiting for us to look closely enough or in the right way. Most dark matter theories assume it's made of heavy, sluggish particles, but what if it's the opposite? Imagine a form of matter so ethereal, it behaves less like individual specks and more like a vast, rippling quantum wave stretching across entire galaxies. That's the radical proposition of fuzzy dark matter, a theory replacing traditional WIMP or axions with particles almost impossibly lightweight, up to a billion times lighter than an electron. These wouldn't clump into dense halos like ordinary dark matter, but would instead form sprawling, interference pattern-like clouds, their wave nature dominating even on cosmic scales. This idea didn't emerge from pure speculation. Observations of dwarf galaxies have long troubled the standard lambda cold dark matter model, which predicts they should swarm with countless dark matter subhalos. Yet telescopes see far fewer than expected, a discrepancy nicknamed the missing satellites problem. Even stranger, the innermost regions of galaxies appear less dense than simulations suggest, a puzzle called the core cusp problem. Fuzzy dark matter offers an elegant fix. If dark matter is wave-like, its quantum properties would naturally suppress small-scale clumping, smoothing out galactic cores and leaving fewer faint satellite galaxies. It's as if the universe's dark scaffolding isn't built from rigid bricks but from a vibrating fluid, its oscillations carving gentler structures into space. The leading candidates for this ghostly matter are ultra-light axions, hypothetical particles trillions of times lighter than their traditional counterparts. Unlike ordinary axions, which behave like discrete particles, these would exhibit quantum coherence over distances comparable to entire galaxies. Picture the difference between raindrops and a mist so fine it blankets a mountain range. Each droplet still exists, but their collective behavior creates something entirely new. In this scenario, dark matter wouldn't just invisibly tug on stars. It would form standing waves around galaxies, with peaks and troughs subtly influencing how matter gathers. Testing this theory requires a blend of astrophysics and quantum ingenuity. Telescopes like the Very Large Array scrutinize the faint hydrogen clouds in distant galaxies for telltale ripples, imprints left by dark matter's wave-like oscillations. Others hunt for unique gravitational lensing patterns that would betray a fuzzy dark matter halo's smooth, diffuse edges. Meanwhile, lab experiments such as the Action Dark Matter E-experiment ADMX adapt their search strategies, tuning detectors to catch signals from axions so light they vibrate at frequencies resembling radio waves. What makes fuzzy dark matter so compelling isn't just its explanatory power, it's the audacity of its premise. It suggests that quantum mechanics, usually confined to the subatomic realm, might scale up to shape the largest structures in existence. If proven, it would mean galaxies aren't just embedded in dark matter, but are floating in something far stranger, a cosmic-scale quantum fog, its gentle undulations guiding the birth of stars and the fate of universes. What if dark matter isn't made of particles at all, but of ancient black holes forged in the universe's first chaotic moments? This provocative idea, known as primordial black hole dark matter, turns conventional wisdom on its head. Instead of hunting for exotic particles, it suggests we've been overlooking cosmic fossils lurking in the darkness, remnants of a time when space was so dense that random fluctuations could collapse directly into black holes. These wouldn't be the stellar mass black holes born from dying stars or the supermassive giants anchoring galaxies. They'd be smaller, stranger, some no heavier than an asteroid, yet packing that mass into a space tinier than an atom. The theory isn't new. Stephen Hawking first toyed with it in the 1970s, calculating how such black holes might form from overdensities in the quark-gluon plasma of the early universe. But it's gained fresh traction thanks to two key developments. First, LIGO detection of merging black holes with unexpected masses, some too heavy to easily explain through stellar collapse. Could these be primordial black holes, survivors of the cosmos's infancy? Second, microlensing surveys like Ogle and Subaru's HSC, which scan millions of stars for brief brightening caused by invisible objects warping spacetime. A handful of mysterious, short-lived events match the fingerprint of asteroid mass black holes drifting silently through galactic halos. The beauty of this model lies in its simplicity. No new particles are needed, just gravity, acting on structures that might have formed naturally in the universe's first second. Picture the cosmos moments after the Big Bang, a seething, ultra-dense soup where quantum fluctuations could twist regions of space into knots so tight they pinched off into black holes. The smallest would have evaporated by now via Hawking radiation, but those weighing between 1 billion tons and a few solar masses could still be around, drifting unseen through galaxies. Their collective gravity would perfectly mimic the effects of particle-based dark matter, tugging stars into unexpected orbits without ever emitting light. But the theory isn't without hurdles. If primordial black holes were too abundant, they'd disrupt delicate cosmic processes, heating interstellar gas with accretion flares or shredding fragile neutron stars in catastrophic collisions. Observations of the cosmic microwave background also place strict limits on how much they could have contributed to the universe's total mass, yet clever workarounds exist. Perhaps most primordial black holes cluster in halos around galaxies, avoiding disruptive densities elsewhere. Or maybe they're part of a dark matter cocktail, mingling with axions or WIMP to collectively explain all the missing mass. The hunt for these relics blends astronomy's grandest and most intimate scales. On one end, gravitational wave observatories listen for the whispers of merging black holes, their masses and spins hinting at primordial origins. On the other, hypersensitive telescopes monitor stars for the telltale flicker of a black hole passing in front, bending light like a lens. Even subtle distortions in the cosmic microwave background might betray their presence, imprinted as faint swirls in the afterglow of the Big Bang. What makes primordial black holes so enthralling isn't just their potential to solve the dark matter puzzle, it's the audacity of reimagining cosmic history. They force us to consider that the universe's greatest secrets might not lie in undiscovered particles, but in the echoes of its earliest instance, when gravity itself could have sculpted darkness into forms we're only beginning to trace. Unparticles defy everything we think we know about particles and dimensions. Picture a world where matter doesn't behave like discrete points, but as something smeared across fractional dimensions, like a shadow that's neither fully here nor there, but somewhere in between. This mind-bending idea was first proposed by physicist Howard Georgi, who theorized that certain hidden sectors of the universe could host particles so strange they don't even fit the conventional definitions of mass or spin. Instead, they'd act like unparticles, exhibiting properties that blur the line between particles and continuous fields. The key to unparticles lies in scale invariance, a property where physics looks the same no matter how much you zoom in or out. Most particles have fixed masses and interactions, but unparticles would scale unpredictably, like a fractal pattern repeating infinitely. Imagine throwing a ball and watching it behave differently depending on the energy of your throw. Sometimes it arcs like a normal projectile, other times it seems to dissolve into a mist of probabilities. That's the kind of behavior unparticles could introduce, challenging the very framework of quantum field theory. So how do you look for something this bizarre? Particle colliders like the Large Hadron Collider might hold the answer. Unparticles wouldn't leave direct tracks in detectors. Instead, they'd reveal themselves through missing energy, events where the energy budget doesn't quite add up, as if a fraction of reality itself had slipped into a hidden dimension. These anomalies could be the fingerprints of unparticles interacting weakly with ordinary matter before vanishing into the unseen fabric of space. Experiments already scour collision data for such discrepancies, especially in the decays of heavy particles like the Z boson or Higgs, where unparticle effects could subtly skew expected outcomes. The implications stretch far beyond colliders. If unparticles exist, they could influence astrophysical phenomena too. Neutron stars, with their extreme densities, might squeeze matter into states where unparticle effects become noticeable, altering how heat dissipates or how magnetic fields evolve. Even the cosmic microwave background could carry faint imprints of early universe interactions with these fractional dimension entities. What makes unparticles so electrifying isn't just their strangeness, it's their potential to rewrite the rules. They hint at a universe where the familiar particles we know might just be the tip of an infinite fractal iceberg, with entire layers of reality waiting to be uncovered in the gaps between what we can measure and what we can only imagine. The universe's first light might hold a clue to one of dark matter's strangest possibilities, particles that carry a whisper of electric charge. This idea, known as magnetic dark matter, suggests that dark matter isn't entirely neutral but possesses a tiny fraction of an electron's charge, along with an inherent magnetic property. The evidence comes from an unexpected place: the EDGES experiment, which in 2018 detected a bizarre dip in the cosmic microwave background at the 21-centimeter wavelength, a fingerprint of hydrogen gas cooling in the early universe. The signal was twice as strong as predicted, as if something had siphoned away the gas's heat. Magnetic dark matter could be the thief. Miller-charged particles, as they're called, would interact just enough to scatter off hydrogen atoms, cooling them through a kind of cosmic refrigeration. Picture these particles as nearly invisible refrigerants, drifting through the infant universe and absorbing thermal energy without leaving a trace. Unlike traditional dark matter candidates, which interact only through gravity, Miller-charged particles would have a faint electromagnetic nudge, not enough to bind them into atoms, but sufficient to leave imprints on the primordial plasma. Their magnetic moments add another twist. Like minuscule compass needles, they could align with ancient magnetic fields, subtly steering the universe's first structures into formation. Detecting these phantoms demands technology that borders on alchemy. Superconducting materials, which lose all electrical resistance at ultra-low temperatures, are the key. Experiments like super-CDMS and DAMIC use silicon and germanium crystals chilled to near absolute zero, where even the faintest jostle from a Miller-charged particle could break Cooper pairs, the linked electrons that enable superconductivity. It's like listening for a snowflake's landing in a silent room. Another approach, exemplified by the proposed Magnon experiment, exploits quantum excitations in magnetic materials. When a Miller-charged particle's magnetic moment disturbs the material's spin waves, it generates detectable ripples, a signature as precise as a fingerprint. The implications of magnetic dark matter stretch far beyond the EDGES anomaly. If these particles exist, they could bridge the gap between dark matter and ordinary matter, offering a rare portal into the invisible sector. Some models even suggest they might form exotic bound states like dark atoms, or catalyze nuclear reactions in stars, altering stellar lifespans in ways we're only beginning to model. What makes this theory so compelling is its double-edged nature. It's both audacious and testable. While Miller-charged particles defy conventional expectations, they leave just enough of a trail to tantalize experiments. Whether the EDGES signal holds up under further scrutiny or fades into cosmic noise, the hunt for magnetic dark matter reveals how the universe's quietest whispers might reshape our loudest theories. Hidden valleys aren't just picturesque landscapes, they're hypothetical pockets of reality where the rules of physics might play out completely differently. In these secluded sectors of the universe, an exotic class of particles called quarks could exist, bound together by forces we've never witnessed. Unlike quarks, which are fleeting and confined within protons and neutrons, Quirks from hidden valleys would form stable, macroscopic strings, strands of energy stretching far beyond the subatomic scale, like invisible threads woven through the fabric of space. What makes quirks so bizarre is their longevity. In our everyday world, particles decay or collide in fractions of a second, but quirks would persist, tethered to one another by a hidden force that refuses to let go. Picture two quirks spawning at opposite ends of a detector instead of flying apart. They'd remain connected by an unbreakable string of energy, leaving behind bizarre, elongated tracks as they slowly reel each other in. These tracks wouldn't resemble the clean, sharp lines of known particles, but would curve, twist, or even spiral as the tension between quirks warps their paths. Detectors like those at the Large Hadron Collider might have already glimpsed these anomalies. Occasionally, collisions produce strange, high-energy events where particles seem to vanish, only to reappear milliseconds later with momentum that defies conventional explanations. Some theorists argue these could be quirks, their strings stretching beyond the detector's active volume before snapping back like cosmic rubber bands. Other experiments like CMS and ATLAS have searched for unusual displaced vertices, points where particles appear to decay unusually far from their origin, as if something invisible were tugging them along. The implications ripple beyond particle physics. If quirks exist, their strings could have seeded cosmic structures in the early universe, acting as scaffolding for the first galaxies. Some models even suggest quirks might form dark matter's hidden architecture, their strings weaving an invisible net that holds the cosmos together. Yet the greatest fascination lies in how quirks challenge our understanding of confinement. In the Standard Model, the strong force binds quarks so tightly they can never escape, but quirks would operate under different rules, their hidden force creating behaviors unlike anything we've seen. Discovering them wouldn't just add a new particle to the menu, it would unveil an entirely new layer of physical law, proving that our universe's rulebook has chapters we haven't even dared to imagine. While WIMP have long dominated the dark matter conversation, there's another contender that flips the script entirely: SIMP, or strongly interacting massive particles. Unlike their weakly interacting cousins, SIMP don't shy away from socializing. These particles don't just pass through each other like ghosts, they collide, scatter, and interact with a force that could reshape our understanding of dark matter's cosmic role. The galactic core cusp problem is where SIMPs shine. Traditional dark matter models predict dense, peaked halos at the centers of galaxies, yet observations reveal smoother, flatter cores. It's as if something's been stirring the pot, smoothing out the expected clumps. SIMP offer an elegant explanation. Their strong self-interactions act like an invisible mixer, redistributing energy and momentum to puff up galactic cores. Picture a crowded dance floor where WIMP glide past each other untouched, while SIMP constantly bump shoulders, jostling the group into a looser, more even arrangement. This dynamic could explain why galaxy cores look fluffier than theories predict. But how would such particles arise in the first place? Here's where the early universe comes into play. SIMP likely emerged from the primordial plasma, not through feeble weak force exchanges, but via intense strong interactions, akin to how quarks and gluons forged protons and neutrons. Thermal production in this seething cosmic soup would have churned out SIMP in abundance, their interactions so vigorous they reached equilibrium before freezing out as the universe expanded. Unlike WIMP, which decoupled early and drifted freely, SIMP might have kept influencing each other far longer, leaving subtle fingerprints in the cosmic microwave background or the large-scale structure of galaxies. Detecting SIMP demands a different approach. While WIMP hunters rely on ultra-sensitive underground detectors waiting for rare collisions, SIMP searchers focus on indirect signatures like anomalous heat flow in neutron stars. These dense stellar corpses could capture dark matter particles, their interiors acting as natural SIMP traps. If SIMPs scatter strongly enough, they'd transfer energy to the star's core, subtly altering how it cools. Telescopes like Chandra are already scrutinizing neutron star temperatures for hints of this exotic heating. The beauty of SIMP lies in their dual nature. They're massive enough to sculpt galaxies, yet social enough to avoid overclumping. Whether they're the true face of dark matter or just another piece of the puzzle, they remind us that the universe's hidden layers might be far more dynamic and far more interactive than we ever imagined. Elko spinners don't play by the usual rules. These exotic fermions transform under Lorentz symmetry in ways that would make ordinary particles dizzy. While most fermions like electrons and quarks spin predictably when viewed from different relativistic frames, Elko spinners twist the math, obeying a modified version of Lorentz invariance that hints at physics beyond the standard model. Their very existence challenges textbook definitions, emerging not from experimental data, but from a theoretical rethink of how spin and symmetry could intersect in uncharted ways. What makes Elko spinners tantalizing dark matter candidates is their stubborn reluctance to interact with light. Unlike standard fermions, which couple to photons via electric charge, Elko particles would be electrically neutral, dark fermions, drifting through the cosmos without emitting or absorbing radiation. But here's the twist. Their unique spin structure grants them a gravitational footprint far stronger than typical weakly interacting particles. Picture a particle that doesn't just ignore electromagnetism, but dances to gravity's tune with unusual enthusiasm, potentially clumping into dense, invisible structures that perfectly mimic dark matter's observed effects on galaxies. The mathematics behind Elko spinners is where things get beautifully strange. Derived from eigenspinors of the charge conjugation operator, hence the name Elko, short for Eigenspinoren des Ladungskonjugationsoperators, they occupy a twilight zone between Weyl and Majorana fermions. While standard spinners transform under Lorentz boosts by mixing their components smoothly, Elko spinners flip signs in a discontinuous jump, a property that initially sparked controversy. Some theorists argued this behavior violated sacred principles like locality or causality, but refined formulations revealed these fears were overblown. Instead, Elko's quirks might encode a deeper truth, that spacetime symmetry isn't as uniform as we assumed, with hidden fissures where new physics could hide. Hunting Elko dark matter would require rethinking detection strategies entirely. Traditional WIMP searches look for nuclear recoils in ultra-pure crystals, but Elko's gravitational affinity suggests subtler approaches like monitoring the vibrational modes of macroscopic objects for anomalous energy deposits. Proposals even exist to exploit their unique spin-gravity coupling in orbiting satellite experiments, where precise accelerometers could catch the faint tug of a passing Elko halo. Meanwhile, astrophysical signatures might lurk in the precise shapes of dark matter halos. Elko's self-interaction properties could produce smoother, more diffuse galactic cores than cold dark matter predicts, aligning with observations that baffle conventional models. The allure of Elko spinners lies in their dual rebellion, against the standard model's particle content and against vanilla notions of spacetime symmetry. They remind us that the universe's rulebook might have footnotes we've yet to decipher, pages where particles don't just differ in mass or charge, but in the very fabric of their connection to reality. Whether they're mathematical curiosities or cosmic game changers, their strangeness is a beacon, illuminating paths to a darker, richer universe than we ever imagined. Dark glueballs sound like something from a physicist's fantasy, but they might be the universe's most overlooked dark matter candidates. Picture a world where the strong nuclear force, the same force that binds quarks into protons and neutrons, exists in a hidden sector, completely detached from the particles we know. In this shadow realm, massless, dark gluons would flit between invisible particles, just as ordinary gluons do in our visible universe. But when confined by their own interactions, these dark gluons could clump into stable, ball-like entities, pure knots of force with no matter at all, drifting through space like cosmic phantoms. Lattice gauge theory, the same computational framework that helped unravel quantum chromodynamics, suggests these glueballs could be far more than mathematical curiosities. Simulations reveal that in a hypothetical dark QCD sector, a mirror version of the strong force but with slightly different parameters, glueballs might form with masses ranging from a fraction of a proton's heft to thousands of times heavier. Unlike traditional dark matter candidates that rely on new particles, dark glueballs emerge naturally from the dynamics of force itself. It's as if the universe found a way to weave dark matter from the fabric of invisible interactions, skipping the need for fundamental matter particles entirely. The beauty of dark glueballs lies in their resilience. Without quarks to decay into, these pure glue states could be astonishingly long-lived, surviving from the early universe to the present day. Their stability hinges on the same confinement mechanism that traps quarks in hadrons, except here there's nothing to escape to. Think of them as bubbles of pure energy, forever bound by their own self-contained forces, drifting unseen through galaxies. Gravitational wave astronomy might hold the key to unmasking them. When dark glueballs collide in the dense cores of galaxies or during cosmic structure formation, their mergers could send ripples through spacetime. Unlike black hole or neutron star collisions, glueball mergers would produce gravitational waves with unique signatures, smoother, quieter, and lacking the electromagnetic afterglow of conventional mergers. Next-generation detectors like LISA, the Laser Interferometer Space Antenna, could spot these subtle tremors, distinguishing them from other sources by their frequency and duration. But the most tantalizing clue might come from the early universe. In the microseconds after the Big Bang, a dark QCD sector could have undergone its own phase transition, akin to how our visible quarks and gluons condensed into protons and neutrons. This transition might have left imprints in the cosmic microwave background, subtle temperature variations or polarization patterns that next-generation telescopes could uncover. Even more intriguingly, dark glueballs could have acted as seeds for primordial black holes, their dense energy knots collapsing under gravity to form the universe's first dark matter anchors. What makes dark glueballs so compelling isn't just their theoretical elegance, it's the way they challenge our assumptions about what dark matter has to be. They remind us that the universe's hidden layers might not be built from particles at all, but from forces we've yet to fully imagine, weaving structures out of pure interaction. And if they're out there, their discovery wouldn't just solve the dark matter puzzle, it would rewrite the rules of what we consider matter itself. In the frenzied chaos of the early universe, when matter was still figuring out what kind of particles it wanted to be, something strange might have gotten left behind, particles carrying fractions of an electron's charge, like cosmic loose change. These aren't the tidy integers of protons and electrons we know today, but relics with charges of 1/3 or 2/3, whispers from an era when the rules were still being written. The idea isn't as outlandish as it sounds. In fact, fractionally charged particles are already part of the standard model. Quarks, those fundamental building blocks of protons and neutrons, carry exactly these charges. But quarks are eternal prisoners, bound so tightly by the strong force they can never wander freely. What if some particles slip through the cracks, evading confinement and lingering into the present day? The search for these fractional fugitives has led physicists to one of the most delicate experiments ever conceived: levitometers. Picture a tiny, supercooled sphere of material, suspended in midair by magnetic fields so precise they can detect forces 1 billion times weaker than gravity. Any fractional charge hiding within the sphere would subtly alter its motion, like a hidden weight shifting in a dancer's hand. Experiments like the Stanford levitometer have spent years scrutinizing bulk matter, metals, minerals, even meteorites for traces of these charges. It's like panning for gold in a river, except the gold might be a single rogue particle with a whisper of electricity hiding in a gram of material. Why go to such lengths? Because fractionally charged particles could be fossils from cosmic phase transitions, moments when the universe's fundamental forces split apart like layers of cooling magma. In those seething first microseconds, topological defects, knots in spacetime's fabric, might have trapped fractional charges like insects in amber. Some theories even suggest these particles could be components of dark matter, carrying just enough charge to interact with ordinary matter in ways that would rewrite the rules of astrophysics. The stakes are high. Finding even one fractionally charged particle would upend our understanding of the universe's infancy, revealing a history more complex than we ever imagined. And if they're out there, levitating specks of dust in a lab might be the first to betray their presence, silent witnesses to a time when the cosmos was wilder, weirder, and far less predictable than it is today. Cosmic strings sound like science fiction hypothetical cracks in spacetime, thinner than an atom yet stretching across the entire universe, left over from the fiery chaos of the Big Bang. These aren't just theoretical oddities. They could be nature's ultimate particle accelerators, whipping matter to energies so extreme they defy every known limit. Picture a string with the mass of a mountain range packed into every mile, vibrating like a snapped guitar string as it slices through the cosmos. Any particle unlucky enough to cross its path wouldn't just collide, it would be catapulted to velocities approaching light speed, gaining energies millions of times beyond what the Large Hadron Collider could ever achieve. This might explain one of astrophysics' most jaw-dropping mysteries, the oh my god particle. Detected in 1991 over Utah, this single cosmic ray carried the kinetic energy of a baseball pitch but compressed into a lone proton. It shouldn't exist. According to the Greisen-Zatsepin-Kuzmin or GZK limit, particles from distant space should lose energy as they plow through the cosmic microwave background, like a marathon runner fighting a headwind. Yet the oh my god particle blew past that limit effortlessly, as if it hadn't traveled billions of light years but appeared out of nowhere. Cosmic strings offer a wild solution. What if this proton wasn't a traveler but a local, freshly accelerated by a passing spacetime defect right in our galactic backyard? The math is even stranger. Unlike black holes or neutron stars, which accelerate particles through electromagnetic fields, cosmic strings would exploit the raw geometry of spacetime itself. As a string moves, it warps the space around it, creating regions where time literally runs at different speeds. Particles caught in these warps would experience tidal forces so violent they'd be flung outward like stones from a slingshot. No magnets, no plasma, just pure relativistic distortion. The resulting energies could reach 10 to the 20 electron volts, enough to make the oh my god particle look tame by comparison. But the real magic lies in the string's potential to rewrite particle physics. At these energies, particles might reveal secrets hidden at scales a billion times smaller than we've probed, unlocking phenomena like quantum gravity or extra dimensions. Some theories even suggest cosmic strings could spawn topological defects, kinks or knots in spacetime that decay into showers of exotic particles, from sterile neutrinos to dark photons. It's as if the universe stashed its most extreme physics behind a cosmic paywall, and these strings are the cheat code. The hunt for evidence is already underway. Telescopes like the Pierre Auger Observatory in Argentina scan the skies for ultra-high-energy cosmic rays, mapping their arrival directions for patterns that might trace back to lurking strings. Others search for the string's gravitational fingerprints, telltale distortions in the cosmic microwave background, or sudden jumps in the timing of pulsars as a string's gravity bends their signals. Even LIGO, designed to catch merging black holes, might someday detect the spacetime tremors of a vibrating string snapping like a whip. What makes cosmic strings so electrifying isn't just their potential to explain anomalies, it's their audacity. They turn spacetime itself into a weapon, forging particles with energies the universe hasn't seen since its first microseconds. And if they're out there, every ultra-high-energy cosmic ray could be a message from the edge of physics, a reminder that the cosmos still has tricks up its sleeve we've barely begun to imagine. Technicolor theories once promised to rewrite particle physics until the Higgs boson stole the spotlight. But what if the Higgs isn't fundamental at all, but a composite particle made of something deeper? Enter technepions, exotic pseudo-scalar particles that could be the smoking gun for a hidden sector of ultra-strong forces binding technoquarks together. Unlike the familiar Higgs, which emerges from a simple quantum field, technepions would be ripples in a cosmic pond of technicolor interactions, fleeting, unstable, yet carrying secrets about how mass itself might be an illusion. Picture technicolor as a supercharged version of the strong nuclear force. Just as gluons bind quarks into protons and neutrons, technogluons would bind technoquarks into composite particles, with technepions being the lightest and most elusive. These wouldn't just be minor players. In walking technicolor scenarios, they'd act as mediators, stretching the symmetry-breaking process over a vast energy range to produce the bizarrely light Higgs we observe. It's as if the universe cheated, using a cosmic funhouse mirror to make a heavyweight interaction look feather-light. Colliders have hunted technepions for decades, searching for their telltale decay signatures. Unlike Higgs bosons, which often decay into photons or W/Z bosons, technepions would favor digit event sprays of quarks and gluons with distinctive angular distributions. The Large Hadron Collider has sifted through mountains of digit data, looking for bumps at specific energies that might betray a technepion's fleeting existence. So far, nothing conclusive, but some anomalies, like excesses in the 750 giga-electronvolt range, have sparked fleeting excitement. The real intrigue lies in walking technicolor's ability to solve the hierarchy problem, the puzzling weakness of gravity compared to other forces. If technepions exist, they'd be part of a dynamical mechanism that naturally suppresses the Higgs mass without fine-tuning, like a cosmic thermostat keeping the universe's energy scales in balance. Some models even suggest technepions could mix with Higgs bosons, creating hybrid particles that occasionally ping detectors before vanishing. Astoundingly, technepions might also bridge particle physics and cosmology. In the early universe, their decays could have generated the matter-antimatter asymmetry we see today, or seeded dark matter through intricate technobaryon interactions. It's a reminder that the Higgs might not be the endpoint of our understanding, but a signpost pointing towards something far richer, a hidden forge where particles are hammered into existence by forces we've yet to fully imagine. Most dark matter theories assume particles once roamed freely in the early universe, colliding and annihilating until only a relic population remained. But what if the truth is the opposite, particles so feeble they barely interacted at all? That's the radical premise of FIMP, or feebly interacting massive particles. Unlike their more sociable cousins, FIMP didn't freeze out from a hot plasma. They froze in, building up their abundance not through battles for survival but through patient, almost silent accumulation. This isn't just a tweak to the usual story, it's a complete rewrite of dark matter's origin. The key lies in the ultra-weakness of their interactions. Picture a crowded party where WIMP are constantly shoving and shouting to stay relevant, while FIMP linger near the refreshments, barely noticed. These particles wouldn't have been forged in the fiery collisions of the early universe, but might instead have trickled into existence through rare decays of other particles, like inflatons, the hypothetical fields that drove cosmic inflation. Every time an inflaton decayed, it could have spat out a FIMP alongside ordinary particles, like a cosmic vending machine dispensing invisible change. Over eons, these dribbles would have added up, quietly flooding the universe with dark matter without ever reaching thermal equilibrium. This freeze-in mechanism solves one of dark matter's quietest puzzles: how to populate the cosmos without overproducing. Thermal relics like WIMP rely on a delicate balancing act. Their annihilation rates must precisely match the expansion of the universe to leave the correct abundance today. FIMPs sidestep this entirely. Their feeble couplings ensure they're never abundant enough to annihilate significantly, so their final numbers depend only on how many were produced by those rare decays. It's like filling a bathtub with an eyedropper, slow, steady, and immune to the risks of overflowing. But how weak is feeble? For FIMP, interactions could be 1 trillion times weaker than the weak nuclear force, placing them far beyond the reach of conventional detectors. This makes them both a theorist's dream and an experimentalist's nightmare. While traditional dark matter searches scour underground labs for rare collisions, FIMP would leave no such traces. Instead, scientists must get creative, looking for indirect signatures like distortions in the cosmic microwave background or anomalies in the decay rates of Higgs bosons, which might secretly produce FIMP before vanishing. The beauty of FIMP lies in their versatility. They don't require new symmetries or exotic forces, just a slight tweak to the strength of interactions we already know. Some models suggest they could be heavy neutrinos hiding in plain sight. Others propose connections to hidden sectors where FIMP act as messengers between our world and an invisible one. And because their production depends on the physics of inflation, discovering FIMP could give us a backdoor glimpse into the universe's first trillionth of a second, long before protons or atoms existed. What makes this theory so compelling isn't just its elegance, it's the way it inverts our expectations. For decades, we've hunted dark matter by assuming it must leave some trace, however faint. FIMP challenged that, suggesting the universe's dominant substance might be built from particles so shy they slipped into existence without ever making a sound. And if they're out there, their silence could be the loudest clue yet to the cosmos's hidden architecture. Neutrinos are already the universe's most elusive particles, but what if they're even stranger than we thought? The Standard Model paints them as loners, barely interacting with anything, including each other. Yet growing evidence suggests they might have a secret social life, engaging in hidden conversations that defy everything we've assumed. This isn't just a tweak to the rules, it's a full-blown rebellion against them, with consequences stretching from the hearts of exploding stars to the frozen echoes of the Big Bang itself. Take supernova, for example. When a massive star collapses, it should flood space with neutrinos, carrying away energy so efficiently that the explosion cools in seconds. But simulations keep running into a problem. Some supernovae seem to cool too fast, as if something is helping neutrinos drain energy even quicker than physics allows. Self-interacting neutrinos could be the missing piece. If these particles scatter off one another in the star's core, they'd create a kind of neutrino traffic jam, delaying their escape and allowing more energy to transfer to the outer layers. It's like a crowded subway where passengers keep bumping into each other, slowing everyone down, except here, the delays reshape the entire explosion. The plot thickens when we turn to the cosmic neutrino background, the relic sea of neutrinos left over from the universe's first second. This primordial fog should be nearly uniform, its subtle density variations smoothed by billions of years of expansion. Yet anomalies in large-scale structure maps hint at unexpected clumping, as if something tugged neutrinos into faint patterns long ago. Self-interactions could explain this too. If neutrinos exerted even a tiny force on one another in the early cosmos, they might have formed invisible currents, weaving wrinkles into the fabric of spacetime itself. These ripples would then imprint on galaxy distributions, leaving behind a fingerprint we're only now learning to read. The implications are staggering. If neutrinos interact beyond the Standard Model, they could be tied to dark matter or even dark energy, acting as cosmic middlemen between the visible and invisible worlds. Some theories propose a secret neutrino sector, where these particles exchange hidden force carriers, dark photons, or other exotic mediators operating in a shadow realm parallel to our own. Others suggest neutrinos might briefly form bound states, like ephemeral atoms held together by forces we've never detected. Detecting these interactions demands ingenuity. Underground labs like Super Kamiok and an ice cube monitor neutrinos from supernova and cosmic rays, searching for anomalies in their arrival times or energies. Even subtler are precision tests of the cosmic microwave background, where Planck satellite data might reveal the gravitational echoes of neutrino self-interactions in the universe's infancy. Meanwhile, next-generation experiments like DUNE aim to recreate neutrino collisions under controlled conditions, probing whether their behavior shifts at energies akin to those inside a dying star. What makes this theory so electrifying isn't just its challenge to the standard model, it's the way it turns neutrinos from passive bystanders into active architects of the cosmos. If confirmed, it would mean these ghostly particles aren't just passing through the universe but shaping it, their hidden hand guiding everything from stellar explosions to the large-scale structure of everything we see. And that's a revolution hiding in plain sight, written in particles we've barely begun to understand. Black holes have long been thought to end in oblivion, a singularity where matter crushes into an infinitely dense point and physics itself breaks down. But what if nature has a built-in escape clause? Loop quantum gravity, a radical rethink of spacetime's fabric, suggests these cosmic monsters might hide something far stranger inside. Planck stars, fiery remnants where quantum effects slam the brakes on collapse, creating objects so dense they blur the line between particle and cosmos. Unlike classical black holes where gravity always wins, loop quantum gravity paints a different picture. Here, spacetime isn't smooth and continuous but woven from tiny, indivisible threads. Think of it as a cosmic mesh where even gravity hits a limit. As matter collapses toward a singularity, these quantum threads resist further squeezing, like a spring compressed to its absolute limit. The result? A rebound effect where the collapsing core bounces back at the Planck scale, forming a Planck star. This isn't a dead relic but a seething ball of quantum spacetime, glowing with energies so extreme they'd make a supernova look like a matchstick. The kicker, Planck stars might not stay hidden behind event horizons forever. Some models suggest their explosive rebirth could rupture the horizon temporarily, releasing bursts of energy detectable as gamma-ray flashes or high-frequency gravitational waves. It's as if black holes have a cosmic eject button waiting to spit back out what they swallowed. Gravitational wave observatories like LIGO and Virgo could already be picking up hints. When black holes merge, their final moments produce a characteristic ring-down signal, a fade out of spacetime vibrations. But if Planck stars exist, certain mergers might show anomalies, echoes or frequency shifts in the ring-down, like a bell chiming in a room that shouldn't exist. Some theorists argue that a handful of LIGO events already show these telltale glitches, though the data remains hotly debated. The implications ripple beyond astrophysics. If Planck stars are real, they'd rewrite the life cycle of black holes, turning them from eternal traps into cosmic transformers, recycling matter through quantum rebirth. They might even solve the infamous information paradox, Hawking's puzzle about whether data swallowed by black holes truly vanishes. A Planck star's rebound could preserve that information, encoding it in radiation or gravitational ripples, like a cosmic hard drive surviving a crash. What makes this theory so electrifying isn't just its challenge to Einstein's legacy, it's the audacity of suggesting that even the universe's most destructive forces have limits. Planck stars remind us that when physics reaches the edge of the known, the answers might not lie in deeper darkness but in a flash of quantum light. What if our universe has a secret twin, a parallel realm with its own protons, neutrons, and even stars, all invisible to us? This isn't just fantasy. It's the tantalizing possibility of dark baryons, a hidden sector of matter that mirrors the familiar particles shaping our world. Imagine an entire periodic table of shadow elements: dark carbon, dark oxygen, even dark water, forming structures just as complex as those in our visible universe, but interacting so weakly with ordinary matter that they've remained utterly undetected. These wouldn't be exotic WIMP or axions, but something far more mundane in composition yet bizarre in implication. A second version of reality, silently unfolding alongside our own. The idea stems from a simple yet profound asymmetry in physics. The Standard Model meticulously describes the particles we know, but nothing forbids the existence of a duplicate set, governed by identical forces yet barely touching our world. In this shadow sector, dark protons could bind with dark electrons via a dark electromagnetic force, creating dark atoms that clump into dark galaxies. Some theories even suggest these dark baryons might collapse into shadow stars, celestial bodies that emit no light yet radiate their own form of dark photons, heat and energy perceptible only to their invisible counterparts. But if dark baryons exist, why haven't they left a trace? The answer lies in the aftermath of the Big Bang. During Big Bang nucleosynthesis, the universe's first few minutes forged the primordial elements hydrogen, helium, and traces of lithium. The precise ratios we observe today are exquisitely sensitive to the density of ordinary baryons. Add too many dark baryons, and their gravitational pull would skew these ratios beyond what telescopes measure. This tightrope act places strict limits on how much shadow matter could exist, likely no more than a few % of the universe's total mass. Yet within these bounds, an entire shadow cosmos could be hiding, its presence masked by the delicate balance of cosmic accounting. The hunt for dark baryons isn't just theoretical. Subtle gravitational anomalies in galaxy rotations or the cosmic microwave background could betray their presence. Even more intriguing are experiments searching for mixed interactions, rare events where ordinary and dark particles might momentarily bridge the gap between sectors. Projects like the neutron EDM experiment at Oak Ridge National Laboratory probe whether neutrons exhibit asymmetries that could hint at couplings to dark counterparts. Meanwhile, astrophysicists scour neutron stars for anomalies. These ultra-dense objects might capture dark baryons, altering their cooling rates or seismic vibrations in detectable ways. What makes dark baryons so enthralling isn't just their potential to double the universe's complexity, it's the way they force us to confront the limits of our perception. If confirmed, they'd prove that reality isn't just stranger than we imagine, but stranger than we can imagine, with entire architectures of matter flourishing just beyond the reach of our senses. And lurking in that possibility is an even wilder thought. If shadow stars and galaxies exist, could shadow life, the cosmos may be far more crowded and far more mysterious than we ever dared to dream. Time crystals shatter one of physics' most sacred assumptions, that all systems must eventually settle into equilibrium. Unlike ordinary matter, which finds peace in stillness, time crystals pulse indefinitely like a clock that ticks forever without winding. First theorized in 2012 by Nobel laureate Frank Wilczek, these bizarre structures don't just exist in space, they're locked in an eternal dance through time, their atoms cycling through states with a rhythm that defies entropy itself. But what if these temporal oddities aren't just laboratory curiosities? What if they manifest as detectable particles flickering at the edges of reality like quantum fireflies? Enter the concept of time quasiparticles, emergent phenomena in condensed matter systems where collective excitations mimic particles, but with a twist. Just as sound waves crystallize into phonons or spin flips become magnons, time crystals could spawn quasiparticles that carry the signature of broken time symmetry. Picture a chain of ions trapped in an optical lattice, laser pumped into a state where their spins flip not because of energy input, but because time itself becomes granular. The resulting excitations wouldn't just move through space, they'd echo through time, creating ripples detectable as fractional charges or anomalous magnetic moments. The hunt for these temporal signatures is already underway. In 2017, researchers at Stanford and Google Quantum AI created a time crystal in a diamond nitrogen vacancy system, observing telltale oscillations persisting long after the driving force ceased. More recently, experiments with superconducting qubits revealed similar behaviors, with quasi-particle-like excitations emerging at predictable intervals, clues that time crystals might indeed birth particles we can catalog. The challenge, distinguishing these from noise, requires quantum thermometers capable of measuring temperature changes smaller than a millionth of a degree, a feat akin to sensing a snowflake's impact on a roaring bonfire. Why does this matter beyond theoretical intrigue? Time quasi-particles could revolutionize quantum memory. Traditional systems lose coherence as entropy washes away information, but time crystal-based storage might exploit these perpetual oscillations to preserve data against decay. Imagine a quantum hard drive where bits aren't stored in fragile electron spins, but in the immutable cadence of a time crystal's pulse. Even wilder, if time crystals exist naturally in neutron stars or other extreme environments, their quasi-particles might solve astrophysical mysteries like the origin of fast radio bursts or the timing anomalies of pulsars. The audacity of this idea lies in its inversion of cause and effect. In our everyday world, energy input drives motion, but time crystals suggest a realm where periodicity emerges from nothingness, where the universe's hidden metronome ticks beneath the surface of reality. If quasi-particles confirm this, they won't just expand the periodic table, they'll add an entirely new dimension to it, proving that matter isn't just what exists, it's also when. Black holes and atoms seem like opposites. One destroys everything in its path, the other builds the world around us. But what if they aren't so different after all? Imagine a black hole so perfectly balanced, its gravitational pull precisely cancelled by an electric charge, creating something entirely new, a black hole atom. These hypothetical structures, known as extremal black holes, could be the universe's most durable dark matter candidates, lurking in the cosmic shadows for billions of years without decaying or colliding. The math behind this idea is as elegant as it is strange. In Einstein's general relativity, black holes are defined by just three properties: mass, charge, and spin. Most real-world black holes are thought to be nearly neutral, their charge negligible next to their overwhelming gravity. But in theory, a black hole could carry enough charge to counterbalance its own mass, reaching a state called extremality. At this precise tipping point, the black hole's event horizon becomes perfectly smooth, its internal singularity hidden behind a barrier so stable, not even quantum fluctuations can disrupt it. It's as if the black hole freezes in place, becoming a cosmic fossil, unchanging, indestructible, and eerily reminiscent of an atom's nucleus. Now comes the quantum twist. If these extremal black holes are small enough, say, the mass of a proton or even lighter, they could bind to electrons or other charged particles, forming structures that eerily mimic hydrogen atoms. Picture it, a micro black hole orbited by an electron, its gravity perfectly balanced by electrostatic attraction. Unlike ordinary atoms, these black hole atoms would be nearly indestructible, their nucleus immune to decay or fission. They'd drift through galaxies like invisible phantoms, their only interaction being the faintest gravitational tug on stars and gas clouds. The real magic lies in how these objects could solve multiple cosmic puzzles at once. First, their stability makes them ideal dark matter candidates. Unlike WIMP or axions, which require delicate symmetries to survive, black hole atoms are naturally long-lived, their persistence baked into the laws of physics. Second, their formation could explain the universe's missing primordial black holes. While most theories struggle to create black holes smaller than a star's mass, quantum fluctuations in the early universe might have birthed extremal black holes in abundance, like bubbles condensing in a cooling soup. Detecting these cosmic hybrids would require rethinking traditional search strategies. Their electric charge means they might occasionally ionize atoms as they pass through Earth, leaving faint trails in underground detectors like super-CDMS. Others have proposed looking for their gravitational lensing effects, microscopic distortions in starlight as these tiny black holes drift across our line of sight. Even wilder, if black hole atoms exist, they could form exotic molecules, their gravitational bonds creating structures far stranger than anything in the periodic table. What makes this theory so compelling isn't just its audacity, it's the way it blurs the line between the infinitely large and the infinitesimally small. Black hole atoms force us to confront a universe where the most destructive forces in nature might also be its most stable builders, where darkness isn't just an absence of light but a hidden architecture waiting to be decoded. And if they're out there, they'd be proof that even in the coldest depths of space, opposites don't just attract, they merge into something entirely new. After exploring 30 of the universe's most mind-bending particle theories, a few stand out as especially promising not just for their elegance, but for how they tackle multiple cosmic mysteries at once. Take axions, those ghostly lightweight particles born from quantum chromodynamics quirks. They're not just prime dark matter suspects. Their discovery could solve the strong CP problem, a decades-old puzzle about why certain particle interactions defy expectations. Then there are WIMP, the heavyweight contenders that dominated dark matter research for years. Even as experiments like LUX Zeppelin come up empty-handed, their theoretical appeal lingers, tying neatly into supersymmetry and the hunt for physics beyond the standard model. And let's not forget sterile neutrinos, the elusive fourth neutrino flavor that could explain everything from weird X-ray signals in galaxy clusters to the universe's missing antimatter. Each of these candidates isn't just a placeholder, they're keys to unlocking entire chapters of cosmic history. What makes this moment so thrilling is the sheer power of our tools to test these ideas. The James Webb Space Telescope peers deeper into the cosmos than ever, possibly spotting dark matter's fingerprints in the way distant galaxies bend light. Upgrades to the Large Hadron Collider will smash protons at unprecedented energies, probing for sussy particles or hidden dimensions. Meanwhile, next-generation neutrino observatories like Dune and Hyper-Kamiok could catch sterile neutrinos in the act, their detectors so sensitive they'd notice a flicker in the quantum darkness. The race is on not just to find dark matter, but to rewrite our understanding of reality itself. So where do you stand? Are axions the universe's hidden architects, or do WIMPs still hold the most promise? Maybe sterile neutrinos are the dark horses waiting to upend everything. The beauty of physics is that the answers aren't just in textbooks, they're hiding in the data, the collisions, the faint signals we're only beginning to decode. Now it's your turn. Which theory fascinates you? Dive into the comments and debate the future of the cosmos. After all, the next breakthrough might start with a conversation.